Hi, this is Francis Sideco with TIRIAS Research. I'm here speaking with IBM fellow Ray Harishankar, who also leads up their quantum safe initiatives for IBM. Talking about some of the NIST standards that have just come out recently, and IBM's thoughts about that and their role in pushing some of the solutions that we really need to get going on because of the timelines that we're dealing with. Just as a background, we're expecting, and not just us, but really various major players in the industry that will have some kind of quantum utility by the 2030 timeframe. And if you dial back in time to that, and with how long it'll take for us to understand where each enterprise, where their different vulnerabilities are, how best to move forward with protecting themselves. That really, we're actually getting into the time frame where these things really need to start happening. So I've asked Ray to join us today to talk about some of the latest developments and where we're at there. So Ray, before we get started, maybe you can go ahead and give an introduction of yourself and your role at IBM.
Sure. Francis, first, let me thank you for the opportunity to have a conversation with you. I always enjoy our interaction, so here is one more opportunity that I couldn't pass up.
Absolutely.
Thank you for introducing me. I am IBM fellow within the IBM quantum team. And for the past 3 years or so, I've been focused on leading the quantum safe initiatives. As part of that, developing business and technical strategy, working with clients to identify their needs, building differentiated technology capabilities that will enable the client's acceleration towards quantum safe and drive industry consortiums to advance the quantum safe awareness and progress. And finally, driving overall thought leadership are all part of my remit in this role.
Awesome. Perfect. Well, so let's delve into that a little bit. So recently, NIST just released some standards around quantum safe and post-quantum computing. Maybe you could tell us a little bit about what some of these published NIST standards entail.
Sure. So to set the context and background, in 2016, recognizing that much of today's cryptography, that is the use of RSA, DSA, ECC, Diffie-Hellman, these are all cryptographic protocols, as you know, they'll be broken by a cryptographically relevant quantum computer. Knowing this, NIST opened a call for submission for quantum-resistant public key cryptographic algorithms. Fast forward to 6 years later, in 2022, after 80 submissions and 4 rounds of evaluation, 4 algorithms were selected. These are 1, Crystal Kyber, which is a key encapsulation mechanism based on the hardness of the LWE, or learning with errors problem. Crystal's dilithium is a signature-based scheme based on the same LWE, but with short integer solution problems, a variant of that. Falcon is number 3, which is a digital signature algorithm based on the difficulty of finding short vectors in NTRU lattices. It's a complex thing, but it's nth degree truncated polynomial ring units. Sphinx, which is the 4th one, is a stateless signature scheme based on security of standard hash functions. 3 out of these 4, that is the first 3, were co-developed by IBM researchers, and Vadim Lubashevsky was one of the creators of all 3 of them. And the 4th, Sphinx, was developed in part by Ward Bulens, who has since joined IBM. So that's all happening in 2022. Now, in 2023, NIST published draft standards for Kyber and dilithium and released them for review. This is when the community gets to comment on it, review it, and they go through several iterations. So just to put these in context, these are some of the first tranche of algorithms. NIST in parallel also called for digital signature on-ramp, for which, for example, from IBM, we have submitted unbalanced oil and vinegar and Mayo, both based on multivariate quadratic equations, and then SQI sign, which is isogeny-based algorithm. Now, the reason I went into all these GORP math terms is to merely make a point that all these algorithms, or at least most of them, are based on different types of difficult math problems. They are not based on the same kind of factorization problem or its variant that the current cryptography depends on. So we are looking at different kind of math problems so that we will not run into the same scenario of having broken one, you have to change everything, right? So that's a summary of the published standards from NIST and their context.
Yeah, and just to clarify a little bit too, what's the main difference between when NIST selects an algorithm versus when they do a standard around that algorithm?
So the difference in my that's a great question, and here's how I would look at it. I talked about going through 4 rounds of testing and evaluation. So these algorithms go through a lot of testing by the community, by NIST themselves, and it's sort of battle proven, so to speak, when you get to the selection point. But a standard way of defining how you can consume it in various scenarios as a consumer of those algorithms has not been defined yet. And that is not as easy a task as it may seem. It is not just about documenting how to use the algorithm, but it's about documenting how best to use the algorithm in various scenarios. And that is where community feedback and help and contribution helps shape how the publication of the standards evolves.
And one other maybe just background clarification. The 4 algorithms that were selected, they're primarily for asymmetrical
That is correct.
applications, right? Not symmetrical. Maybe you could just give a little bit of what the difference is and why the community is focusing on the asymmetrical side.
That's a good point. So again, to set the context, there are 2 types of cryptography that's being used prevalently now. Asymmetric cryptography, as called out, and obviously then symmetric cryptography. Now, symmetric cryptography is primarily, and I'm simplifying this a bit to make it simpler. Symmetric cryptography is for data at rest, whereas asymmetric cryptography is for data in communication. So what that means is any digital communication that we uses asymmetric cryptography. And asymmetric cryptography is based on mathematical problems that are based on factorization of large prime numbers, of large numbers, sorry. And that problem hitherto has been, or it still cannot be solved by classical computers. However, by applying Shor's algorithm on a quantum computer, one can break that in a matter of hours or days, depending on the capacity of the quantum computer. That is the key point behind why we are saying asymmetric algorithms need to be replaced. So that may beg a question. So what about symmetric algorithms? Is there an algorithm that on quantum computer can break it? Well, there is an algorithm, man, the name escapes me.
No problem. This is just for context anyway. But
no, I know. We got to edit this out somehow. But it's Shor's algorithm and Grover's algorithm. Thank you.
Yes.
So Grover's algorithm is again another algorithm that runs on quantum computer, and that will only allow or yield a quadratic speedup of the algorithm, whereas Shor's algorithm offers clearly a polynomial time speed up, and that is achievable and on a quantum computer. And so the simplest way is a symmetric algorithm can be extended, or its life can be extended by going from AES 128 to 256, and you could buy yourself another 20-30 years.
Right.
So it's not a big worry right now, but asymmetric algorithm certainly is a concern, because once a cryptographically relevant quantum computer becomes available, all asymmetric algorithms are exposed.
Perfect. So let's delve deep into these standards, right?